Good morning, all of you. So, in today's class, we will see assumptions of kinetic theory of gases. Okay, yesterday we have started this chapter. So, what are the assumptions of kinetic theory of gases? That is KTOG. In short, if you will write KTOG, it means what? Kinetic theory of gases. Keep it in mind. So, let's see. First assumption. So first of all, in the thermodynamics, we have learned thermodynamic variables, pressure, volume, and temperature. Now, in this chapter, we will see the relation of that macroscopic particles or macroscopic properties, we can say, with microscopic properties of gas. For example, macroscopic means pressure, temperature with respect to or with speed, momentum, and kinetic energy. Their relation we are going to learn in this chapter. So, in simple words, relation of pressure, temperature with speed, momentum, and kinetic energy. Got it? So see here, it relates it relates macroscopic macroscopic properties in bracket pressure, comma temperature to the microscopic properties of gas molecules. To the microscopic properties. Microscopic properties means of speed, momentum, and kinetic energy. In bracket, speed, momentum, comma kinetic energy, etc. of gas molecules. राइट तो पहला पॉइंट या तो आप इसको जनरल पॉइंट बोलो बिकॉज दिस इज नॉट assumption, so we can just keep it as a general point, and from this we will start assumptions. These assumptions of kinetic theory of gases are just kinetic theory of gases. It relates macroscopic properties with microscopic properties. And let's start now. First assumption, see here, every gas, this is now assumption started, every gas consists of extremely small particles known as molecules. Molecules and size is negligible in comparison to in comparison to intermolecular distance. That is 10 power minus 9 meter. This is your assumption number 1. So what is this assumption? See, if suppose we are having any gas, so this gas consists of extremely very small particles whose known as molecules, and their size is very negligible in comparison to intermolecular distance. Okay, this is your first assumption, and that is how much distance is 10 power minus 9 meter. Second assumption, the molecules of a gas, the molecules of gas are identical, मतलब सब सेम है, identical, spherical, rigid and perfectly elastic, and perfectly elastic point masses. Okay, the molecules of a gas are identical, spherical, rigid and perfectly elastic point masses. Okay, this is what second assumption. Next, third assumption of this kinetic theory of gases. First, you note down this if you did not write. Okay, note down this. Now you will ask me one question, sir. Molecules of gas are identical. It means every gas has identical molecules only. For example, suppose H2 gas is there, hydrogen gas and oxygen gas. Then hydrogen gas molecules and oxygen gas molecules are identical? No, not like that. Same gas, same molecules. Different gas, different molecules. Keep it in mind. Okay. So I'm writing in the bracket same gas, same molecules. Same gas, same molecules. Different gas, different molecules. Okay, keep it in mind. So next assumption, the volume of molecule, the volume of molecule is negligible in comparison to the volume of gas. In comparison to the volume of gas. It means how? Suppose now you are having here This is the gas filled in this container. Suppose this is gas. Now you see this one molecule. This one molecule is having very, which I have rounded with the red color. I am rounding it. You can see. Yes, inside this one molecule is there. Okay. So this molecule volume is very negligible as compared with this complete volume. That is what the meaning of this third assumption. And here, how much they have given? C phi of molecule is equal to 0.014% of volume of gas. That's why we are saying that molecule volume is negligible as compared with gas volume. Next assumption, fourth number. Density of gas is constant. Density of gas is constant at all points of the container. At all points of the container. Okay, everywhere mass per unit volume is same. That's why otherwise suppose gas will finish means gas will, what you can say, heavy at down and all, or gas will come out fast and slow. That is not at all the issue. Okay, so everywhere density is same. Density is same at all points. Next assumption, molecules obey Newton's laws of motion. You know Newton's laws of motion, है ना? Newton's laws of motion, and their motion is isotropic. Their motion is isotropic. Next assumption, suppose now these are the two molecules. See here, I can say I am drawing just diagram, and now this time is, let us suppose t. Now this is collision, okay, here, and this time is suppose t dash. This time t is what and t dash is what? Time t is time during collision. T is what? Time during collision, and t dash is what? Time between two successive collisions. Time between two successive collisions. T dash is time between two successive collisions. So T is negligible compared with T dash. T is negligible compared to T dash. What you understood from this? What you understood? When the two gas molecules are colliding, that distance is negligible as compared with between two, that time between two successive collisions. Okay. It means T dash is more. Okay, finished. Next assumption, 7 number. And one more point here, you see always number of collisions per unit volume in a gas remains constant. Okay, next. Seventh one, no attractive or repulsive force. No attractive or repulsive force. No attractive or repulsive force acts between two gas molecules. Acts between gas molecules. If suppose there is attractive or repulsive force, you might have seen a gas cylinder dancing at midnight, isn't it, right? Oh, something is happening inside. There is pulling and pushing in between the gas molecules or in gas cylinder, right? It is like fighting between them, isn't it? But is it happening? No. So that's why there is no attractive and repulsive force between the two gas molecules or between gas molecules. And last one more assumption is there, that is molecules constantly molecules constantly collide with the walls of container due to which their momentum changes. Due to which their momentum changes. Okay. And therefore, due to this, pressure is exerted by the gas molecules on the walls of container. Due to this, pressure is exerted by gas molecules on the walls of container. Due to this pressure, or due to this pressure is getting exerted on the walls of the container. Okay, this is what assumptions of kinetic theory of gases. Yes, right, understand. So next, now pressure of an ideal gas, let's find out. pressure of an ideal gas. Pressure of an ideal gas. So for that, let me draw first diagram. Okay, like this you can draw the diagram. Okay, and now this is A1, this one is A2, and now this is suppose X, this one is Y, and this one is Z. And let us suppose so suppose the length of this container or box is L. Capital L. Now this is a cubical container of length L and there are N molecules. Now this is suppose first molecule I have taken, and this molecule will go like this with velocity Vx. With velocity Vx. This will go and collide on this wall, and again it will come back. And then this time its velocity is what? Minus Vx. Or you can just write Vx only because its velocity in magnitude is not going to change. So this will after collision, this is also velocity is what? Vx, but in opposite direction. Yes or not? After colliding this. Right? It will come something like this. Colliding and coming like this in the opposite direction. Okay. Now So you are having how many molecules? Let us suppose n molecules, and in a cubical container, of length L, cubical container of length capital L. So now this molecule is there. Yes, this molecule is free to move in any three direction: X, okay, Y or Z, and this side we have taken as a X, right? So on along each axis it has velocity. What is that? Let's denote. This is Y axis. This one is X according to our diagram, and this one is Z. So along this axis you are having velocity Vy. Along this you are having Vx, and along this you are having Vz. Okay. So if I want velocity, can I write like this? So V bar is equal to Vx I cap, Vx I cap plus Vy j cap plus Vz k cap. And therefore if I want magnitude of V bar, you will get under root of Vx square plus Vy square plus Vz square. Okay, Vx square plus Vy square plus Vz square. And now, due to random motion of molecule, what happens? Due to random motion of molecules, here Vx is equal to Vy is equal to Vz. Means all velocity along all axes is same. And therefore, if I want V square, then you can see here. This is if I will square it, then you will get what? Either 3vx square or 3vy square or whatever it is. If suppose I will do this and I will substitute vx is equal to vy is equal to vz, then you will get here vx square plus vx square plus vx square, that is equal to 3 vx square. Or even if you have substituted y everywhere in this equation after squaring, so you will get like this 3 vy square also, or even you will get 3 vz square also. This is what your v square is, right? So note down. Next, now change in momentum when molecule collides elastically. Next one in this only, change in momentum when molecules collide elastically. You can see in the diagram, see this is having suppose mass m. It is going and coming back. So if I want to find change in momentum, what I will do? Delta P is equal to minus mvx minus of mvx. So that is equal to how much? Minus 2 mvx. Why you know delta P is equal to what? mv minus mu. So this is what? M minus u minus of mu. तो क्या होगा? minus mu minus mu. So that is equal to minus 2 mu. Yes or not? Same case here also. Here just u is nothing but what? Vx. So you got delta P is equal to minus 2m Vx. Now time between two successive collisions. Next point or next I am going to find, that is time between two successive collisions. Time between two successive collisions is equal to distance traveled by molecules between two successive collisions divided by velocity of molecule. Velocity of molecule. So distance traveled is what? If you will see the diagram, while going L, while coming L. So how much this is? 2L divided by what is the velocity of molecule is Vx. So therefore what you are getting, delta T value, delta T is equal to 2L by Vx. Now let's find out frequency. So what I am going to find now? Frequency. So frequency is nu suppose, and it is equal to 1 by delta T, reciprocal of time. This is equal to what? Vx by 2L. This is we got frequency. Now from Newton's second law, from Newton's second law, F is equal to delta P by delta T. You know this. That is equal to delta P value is what you are having, 2m Vx. No need of minus sign, 2m by Vx divided by 2L by Vx. So this Vx is going up, this 2 and 2 will get cancelled. So what is your answer? M Vx square divided by L. This is what your force is. And if you want to find only on x-axis, then F of x is equal to M by L summation over Vx square. And for n number of molecules, for n molecules, Fx is equal to n into M by L phi x1 square plus phi x2 square plus so on plus up to phi xn square. Okay, and therefore if you want force exerted, Fx is equal to M into n by L into Vx bar square, where Vx bar is what? Vx bar square is mean square of x component of velocity. Mean square of x component of velocity. Okay, this is what force exerted. but we want pressure, yes or not? Now we got just a force, now we have to find pressure. So see, now pressure is defined as pressure is equal to force per unit area. Pressure is equal to what? Force per unit area. So therefore pressure along x-axis is equal to Fx divided by A, and that is nothing but mn by L into A, because A is down only, into Vx bar whole square. Can you see here? Just see. You got already Fx, just you will divide with A, you will get the pressure. And therefore area into length is volume. So therefore Px is equal to mn by capital V into Vx bar whole square. This is what your pressure you got. Yes. But for any molecule, you see, for any molecule, V bar square is equal to Vx bar square plus Vy bar square plus Vz bar square. And we know Vx, this is the average mean square, we can say. Bar is not vector, this is mean square of x component, we can say. So Vx bar square is equal to Vy bar square plus Vz bar square, and this is equal to, this one I should make it here plus, so this one is equal to Vx square is equal to Vy square is equal to Vz square. If it is equal, then V bar square is equal to what you can write, 3 Vx bar square, and therefore either Vx square or Vy square. Similarly, you can write like this also, 3 Vy bar square, or even V bar square is equal to 3 Vz bar square, and therefore can I write like this, Vx square plus is equal to is equal to Vy square is equal to Vz bar square is equal to V bar square divided by 3. Yes, can you see? Okay, so this is what your velocity is, and therefore total pressure, if I want this, therefore total pressure P is equal to, this is the biggest derivation from this chapter, remaining is very easy. Inside the container, that is P is equal to, already you got this mn by V is volume, and this just Vx bar is equal to what? Now V bar square divided by 3, and therefore you can write direct, therefore P is equal to 1 by 3 mn mn by phi into phi RMS whole square. This is what your pressure formula is. Okay. Now this phi bar and phi RMS you got. What is the relation, sir? So you keep it in mind. Phi RMS is equal to under root of phi bar square. Phi RMS is equal to under root of phi bar square. So if you take square root, you will get the same thing. Okay, right? And one note point ahead. So note point phi is equal to 1 by 3 m n into phi RMS whole square. This is the first one. And P is dial proportional to m n t by phi, because phi RMS square is dial proportional to temperature. So therefore, this is pressure is dial proportional to this. And what terms are there inside? You see, m is where m is mass of the gas, n number of molecules, phi is volume of gas, phi is volume of gas, and T is temperature. Okay. So these velocities we are going to learn tomorrow. Different velocities, RMS velocity, average velocity, and all these things in the tomorrow's class. So for the today's class, or just for today, you just see this derivation very carefully and ask me out if you have any. Okay. Bye for today.